Well, hello, and we're going to be talking about today mechanical properties of materials. So, physical properties of materials are a material's response to some environmental variable, such as light, temperature, gravity, electromagnetic field, or a mechanical force. So, in this presentation, we're going to focus on the mechanical properties, which is a subset of physical properties that deal with the material's response to a mechanical or applied force. We will discuss some of the methods of testing materials for these forces. So first I'm going to go with a word about notes. So note taking in your journal, you should be hopefully have a journal or some note sheets that you're keeping in a 3-ring binder, some way of doing that. So notes should be neatly entered. You should be expressing a clear thought. Should be able to look this up in, say, a week or so and know what you were talking about. The key about note taking, though, is this: you have to express the clear thought so it jars your memory to bring back those thoughts that you were thinking or the information you were taking in at the time you were taking the notes. Why take notes? Well, it's useful information to keep track of, helps you in understanding, helps you in writing, and it can improve your writing skills, helps with your memory. So these are memory joggers. A lot of these notes are to help you, and they can help you with exams because when we do get in class and we start having exams, I will give you the opportunity to have an open journal or open notebook during the test or quiz. Notes should include facts, stats and formulas, paraphrases, summaries of ideas, personal understanding or questions. And when I'm saying understanding or questions, you should be noting down things that strike you in a presentation or something you don't understand necessarily. So you put down a question. What did he mean when he said this? What did she mean when she said this? And then later on, when you get an opportunity, especially at the end of my presentations in our Zooms, I give you the opportunity to ask questions and clarify. And even during those, ask questions to clarify, to get them better in your mind what it is that I'm talking about. So, how are you doing so far? Right now, you should have 2 things noted. Notes should be, which are neatly entered and express clear thoughts. 5 things notes should include: facts, stats and formulas, paraphrases, summaries of ideas, personal understanding, and questions. And let me go back to paraphrases. Paraphrases should be things in your own words, taking maybe a whole bunch of things I said and boiling it down to something that you're using your own words to express. So, mechanical properties. Basically, there are a subgroup of physical properties. They are the response to force or stress. So you might have, a material, and it may have lots of different properties. You may be able to get all the physical properties of, the material is kind of a brownish color, it's kind of grainy, it doesn't hold together, but when you want to know the mechanical properties of it, you're going to have to apply either a push or a pull. You're going to have to do a mechanical force to it. All right. And then we need to look at the term stress. Stress is force causing a deformation or distortion. It's measured as a force per unit area. So it is pounds per square inch, newtons per square meter. So it is an amount of force against a certain surface area, and that is stress, an applied force. Okay, so physical properties, characteristics of materials possessed by itself, in and of itself. Okay, they're a personal trait. So in general physical properties, you would say that gentleman has brown hair, that lady has blonde hair. That person's tall, that person's short. It would be something that you would notice about them. They are 6 feet tall. This person's 5'6". So you can be measurable. It can be something noticeable or measurable. Okay, and then it could be a response to energy, like light, or electricity. All right, but mechanical properties, as we said, the reason why we care about mechanical properties, because, well, we can use these properties to help classify and identify materials. Okay, like any material properties, they can be used to classify and identify materials, sort them by how they respond to certain physical forces. Okay, most common properties that we're going to look at mechanical are strength, ductility, hardness, impact resistance, and fracture strength. One of the things we want to talk about is workability. And workability is not a singular mechanical property. It is a combination of malleability and ductility. So malleability is basically being able to, how well you can flatten it, how well you can shape it with, say, a hammer. How well can you beat it out into a shape without it just being destroyed? And ductility is the ability to be drawn out or be pulled, stretched, extruded, those kinds of things. As you can tell by this one picture here, you've got rollers, you're rolling out, so you could be pulling this in as a wire, pulling it, or you could be rolling it out in a metal roller, or a press, as it's called. And that ability to stretch it out and roll it or to hammer it, those both together, malleability and ductility, give us workability. So the more workable something is, the more or higher amount of malleability and ductility it has. All right. So the opposite of that, excuse me, the opposite of that is brittleness. Brittleness is a piece of chalk snapping in two, something that's not going to hold together when hit or when stressed. It's not going to bend. It's going to just break. Now it could be hard, and we could talk about hardness, but which we will. But it can be hard, but at the point where it starts to deform, it doesn't have much deformation ability in it. It just snaps. So when it fails rather catastrophically. All right. But hardness, on the other end, is a material's resistance to denting or scratching. So you can scrape it, and if it's harder than the material you're scraping with, then you're going to leave a scratch or a dent in it. If you're not, then it's not going to, if it's something softer. All right. So here I have a couple of pictures of the hardness testers, which you can use to scrape or to press into something to dent it, and that would be testing the hardness factor. Usually you're going to have things like the Mohs scale, M-O-H-S, Mohs scale, and it's going to be a relative scale from 1 to 10 on different materials, or you can do a Rockwell hardness test too. Those are different types of hardness tests. Okay, so mechanical properties, some examples are elasticity, the ability to return to an original shape after being deformed or stressed. Rubber bands are a perfect example of elasticity. You can stretch them and they come back, and stretch them and they come back. And once you've reached what's called the elastic limit, then it wouldn't come back as in the same exact shape. It might be stretched out a little bit. And plasticity is an ability for the material to retain a new shape after it's been deformed and stressed. So plastic deformation is when you've pushed into something and then when you let go, the dent stays. A real good example of this is basically a car bumper. A car bumper, if you bump against it, it gives and it comes back. That would be elastic deformation. But if you bump it hard enough, then the bumper dents in and doesn't come back. That would be plastic deformation. All right. Wet clay ball or a piece of saran wrap is another good example of that, where you drop a wet clay ball and it dents. So on an atomic scale, elastic deformation, you can see here that this is the original shape of the atoms. Here, a small load is put on it. It is being pulled, and so it stretches, and those atoms stretch apart a little bit. And then when released, it comes back, and there's an elastic deformation. This right here, the elastic deformation, because it goes back to the original after you release it. Plastic deformation, on the other hand, here's the same thing, initial atomic line up here. Then when we put a large load on it and we've really pulled it and all these bonds are slipping and it's starting to stretch, then when we unload it, it didn't come back to this over here. It became elongated. It became longer. Okay, so it didn't necessarily go back. So you can see here, here's your line. This is the original length. This is you stretching it, and then when you let it go, it goes back, but not all the way back. So that would be plastic deformation. More mechanical property examples: toughness, the ability to absorb energy, resistance to fracture. So it's able to absorb the energy and not fracture. So that would be toughness. Strength, there's several that we call strength. So there's resistance to distortion by stress or force. And it depends on the direction that the strength you're measuring is. Whoops, went too far. So you have tensile strength, compressive strength, torsion strength, bending strength, shear strength. It's all depending on what type of force that you're applying to it, that the strength you're measuring. All right, so in this particular case, you have tensile strength or tension, which is pulling. So these are your arrows of force. So the force is going away from the middle, and that is tension. Here we are under tension because things are pulling away from it. Okay, tug of war, slingshot, those are examples of tension. So compression, on the other hand, obviously, is things being squeezed together. So you have your two forces going towards each other, and in the middle is where the compression is, where here's in the middle is the tension being pulled. And these two pictures here kind of show when you're under tension, you tend to thin in the middle. This is the original shape here. Here's the shape of it when it's being fully under tension. So you're stretching it and pulling it, and it's thinning in the middle. Whereas under compression, it is thickening in the middle because you're pushing towards the middle, and it starts to thicken here. Examples of that are bed springs, can crushers. Bench vise is a really good one, as you're squeezing it. So, and that's basically it. I mean, it's a squeezing force, compression, whereas tension is a pulling force. Then we go to torsion, which is a twisting force. You can think about wringing out a towel, wet towel, and then you've got shear. So the thing about this is you've got it rotating. So you've got a force going this way and a force going this way, and they're going opposite. But this is a tortuous line here, or tension, or torsion. I mean, a tensile. Sorry, I keep it in tension. A torsional motion. So it is a twisting motion, whereas shear is a lot like compression and tension in that you've got either going towards each other, the forces, or away from each other, but they're not on the same plane. They're not, see here, this one's going here, this one's going here. They're not lined up, and neither are these two lined up. So that is shear. A perfect example is scissors. Scissors, the tongue of a trailer. So here you go. Torsion is a twisting motion, like turning out a wet paper towel. Or shear is when you got a force coming this way, and then here's the shear zone where it's being sheared. And scissors is a great example. And here is what's called a shear pin. And this is designed to give. So right in here is a certain amount of shear force that's going to break this. And it's designed as a safety device, because you don't want, in case there's something you don't want to get overstressed or over too much force buildup in it, then this will shear before it gets to that point and let go. So let's do a note check. How are you doing on your notes? Are you marking down the different forces, shearing and torsion and compression? Okay, good. So how about a graphic to help? Here we go. This graphic, and you'll be able to, you can also look this up in the, I think whatever week this is, week 8. But this diagram is in there. This is the mechanical properties chart. And so this is a visual. Here's your tension. Of course, here's your dotted lines from when you're pulling. It's going to start to thin the middle. Here it's starting to thicken in the middle. Shear, where you got two forces, it could snap, and this is the shear zone right here where the forces are going opposite direction. Okay, hardness, you're denting or scraping it. Torsion, you got this torsion forces going in circles here. Impact, you're hitting it. Now, we didn't talk much about this, but flexure it's bending. A material's tendency to bend under force and its ability to bend under force without breaking. And then we go to fatigue. Fatigue is when you go bending back and forth, what's called cyclic loading. You got a load, you're letting it go. Again, loading is also stressing, or a force on it is a load. So there's many terminologies used here, but in mechanics, it's used if you're putting a force on something or a weight on it, it's referred to as a load. So when you're loading this up in a cyclic manner, cyclic load, you could build up to fatigue, where it's going to be fatiguing you. And when you get to like a piece of metal and you get to metal fatigue, that's when it snaps and breaks. And you've probably done this before. You've taken something, you bend it back and forth, back and forth, back and forth, back and forth, and then finally, eventually, the cracks start to build, and then finally it goes snap. So when you're talking about mechanical forces, we usually look at stress and strain curves. So basically, a stress and strain curve is stress, which is a cause. Stress is the cause, strain is the effect. Stress is the force that causes deformation or distortion. Strain is the change that's caused by the stress. So that deformation, that deforming, or usually a lot of times it's in the terminology is it's elongation or it's a shortening of whatever the material is. So either you've stretched it or you've pressed it and shrunk it. So that change in shape due to stress is referred to as strain. Then another word for it is deformation. Deformation is just a general term for the change in shape of something. It's deformed, but strain is directly related to stress. Okay, it is the deformation caused by stress. And remember, stress isn't just a force; it's the applied force to an area. A lot of terms bouncing back and forth, and they sort of mean the same thing, but there is a difference to them. So a stress is a kind of force, but it's not force. Stress is that force applied to an object. Okay, and strain is the change or the deformation that's caused by the stress. Okay, and here's what a stress strain curve looks like. Okay, it's all about the shape of it. And this is how you use mechanical properties to look at differences in materials and your ability to categorize it or sort it. So unfortunately, yeah, this one got kind of messed up here, this slide. But the straight line region here is what's referred to as the elastic region. And then once it starts to bend right up in here, and that's called the plastic region. So we've got strain down here, so that's the change in the shape. And we've got the stress or the applied force up here. So when you're doing the applied force, as it's being forced, it's absorbing that energy and it's starting to strain. So in this particular case, right about here, it's starting to either elongate if it's a tensile strength, or it's starting to shorten if it's a compressive strain. And this is just the change in the shape of the material responding to this stress. So when you have something that's brittle, it's going to come up and then it's going to snap. Now, it may take a lot of stress before it gets to that point, but it doesn't have a lot of bend to it, and the curve that is. So now here you've got a low yield. This one's a high yield because it goes way up here before it's such a yield. But here you got a low yield point, low yield strength, because it doesn't go nearly as far in the stress area before it starts to deform. But it deforms and deforms and deforms and deforms and deforms until finally it breaks over here. When the line ends, that's when it's failed. All right. So Obviously, a brittle object, obviously over here, a ductile object. So here's just a set of curves. And you're noticing that ceramics and glass, which are mostly brittle, tend to have something that looks like this, like that here too. And then metals, you get a little bit, because you got some ductility and malleability, it's going to deform until finally it breaks. And then polymers or plastics, depending on, and this is a generalized category, but depending on if it's more elastic than plastic, it will give easier, but then it'll keep going and deform until finally it breaks way over here. So the amount of strain it can take, which is the deformation of it, then that's what's going to keep this line going farther and farther. But you'll notice it didn't get up as high. The stress comes up here, and then it starts to deform. Whereas this one doesn't start to deform until here, and this one doesn't start to deform, but then fails right away once it does, but at a pretty high stress. So in summary, mechanical properties are a subgroup of physical properties. A material's response to an applied force. So the stress, the applied force, is put upon it, and this is how the material responds to that or strains to it. And then it can be used to help us classify and identify materials. So that's what we have for today, or at least this session, I suppose I should say. Hopefully you have picked up some good notes on this, and you'll review them, and hopefully it'll be good for you. All right, that's it.